Hello everyone, and welcome to this week's Cassandra community webinar. Delighted to welcome back Aaron Morton, the co-founder and principal of the Last Pickle. He is also a committer on the Apache Cassandra project, extremely well known in the Cassandra community. If ever you are on IRC or the mailing list, asking a question, odds are Aaron has answered one for you. So welcome back, Aaron. And just one piece of housekeeping, if this is your first webinar with us, Aaron will be taking questions at the end of the session. Please use the Q&A tab inside of WebEx and ask your question there, and we will get through as many as we can at the end. So Aaron, exciting times, I believe, at the Last Pickle. You are expanding, business is good. We look forward to your webinar today. Take it away.
Thanks, Christian, and good morning to everyone. As Christian said, I'm the co-founder and principal consultant at the Last Pickle, where we help customers deliver and improve Apache Cassandra-based solutions. We're all DataStax MVPs, and I'm a committer, the maintainer for the Hector library, and a committer for the Apache User Grid project, and we're based in New Zealand and America. What I wanted to do today was talk about large nodes. Now, when we're talking about large nodes, it's important to have some sort of context for what's large. After all, we're supposedly dealing with big data. A few years ago, I started saying, as a rule of thumb, don't put more than 500 gigs of data on a node. Initially, this was just talking about EC2, and the reasons had to do with a little bit of what it was to be running on EC2. So what sort of throughput could you get on the networking, the performance of your disks. It's bound up in a bunch of operational concerns, and these are the things that we're going to talk about today, and how these operational concerns have disappeared a bit over the intervening years. But in general, we're talking about nodes with over 500 or 600 gigs of data per node. Nowadays, we can talk about nodes in the 1 to 3 terabytes of scale. That's our framework. But we're also talking about nodes that have more than 1 billion rows per node. So 1 billion rows over all of your tables. Now, that could be a case where you've got multiple terabytes of data. You can also pretty easily get to billions of rows per node just by having lots of small rows. So you might be recording something like website hits or website logs or something like that. You can pretty easily get to 1 billion rows. As I said before, version 1.2, there are a number of operational and performance concerns that we had to worry about dealing with nodes in this sort of category. Over 500 or 600 gigs, over a terabyte, and over 1 billion rows. Post 1.2, there are fewer operational concerns. Most of them are still there, but they're decreased in terms of their impact. But it's important to understand why we were concerned about these things in the beginning, because it's good to have an understanding about why changes are made in Cassandra. And some of these operational concerns are still there. And if you grow fast enough, you will still run into them. So we'll look at those issues we had pre-version 1.2. And we'll look at some of the workarounds that we had just to give us some context about why changes were put in versions 1.2 and beyond. And we'll look at a couple of the issues coming up in 2.1 that are going to improve things even further. Memory management was always was always a big concern. There are some memory structures in Cassandra that grow with the number of rows and the size of data that you've got per node. And the first one we'll look at here is bloom filters, and these are probably the most well-known and least understood data structure that we have. We use these to test if a row key exists in a particular SS table. it will tell us either that the row key definitely does not exist or it does exist with a certain probability that that's false. We hold this in memory. It's essentially just a bit set. And by keeping it in memory, we dramatically reduce the amount of disk I/O we have to do. So the size of this structure depends on the number of rows in a particular SS table, and a property setting called the Bloom filter FP chance. And this is a setting that goes on the table. But we don't know exactly how many rows we've got in an SS table. We do the first time when we write it out. We know when we flush the disk, we're going to write 100 rows into this SS table. Over time, though, we just have to guess. We estimate based on some things that happen in compaction. We'll look at that. So internally, our Bloom filter was implemented as a two-dimensional array of longs. Again, we treat it just as a bit set. This was just how it was implemented. And if we look at the memory usage for this guy, along the bottom here, we've got millions of rows. And when we hit 1 billion rows at the right-hand side, the gray line indicates when the Bloom filter FP chance is 0.01, which is the default when we use the Size TieredCompaction Strategy. At that setting, we'll use approximately 1,200 megabytes of space just to hold the Bloom filters. If we're using the LeveledCompactionStrategy strategy when your column family is created, the Bloom filter FP chance defaults to 0.1 or 10%. And you can see on the red line there, that's approximately half the size that we have for the 0.01. So still about 600 megs, all stuff that we have to keep in memory. We also have compression metadata that we have to store in memory. Now, when we take your data and compress it, we need a map that tells us, oh, this chunk of uncompressed data actually starts at this position in the compressed data stream. So when we take the offset for the start of your row from the index component of the SS table, we know where to look. The size of this depends on the size of the uncompressed data, and it's held in memory as well. Again, it was implemented as a two-dimensional array of longs. In this case, though, they're actually used as longs. We just have the longs and we offset in based on the offset from the SS table. The size of this depends on the amount of data we're trying to compress and, to a degree, the compressor that's in use and the size of the chunks that we're compressing. So if we've got a terabyte of data using the Snappy compressor, we could expect a couple of 100 megabytes of compression metadata. Again, all stuff that has to be held in memory and can't be released. We also have index samples. So in our SS tables on disk, the three most important files for each SS table are the data component, the Bloom filter in the filter DB, and the index, the primary index. This is your row keys and their offset into the data DB component. Now, in memory, we hold a sample of every 128 keys by default. And this essentially gives us a skip list or an index over this. So when we want to find your row key for a read, we look through our index samples in memory. That gives us a page that may contain the key that you're looking for, and we drop down to disk and do a read. Of course, if we get a hit on the key cache, we don't do this part, but if we get a key cache miss, we do this. So the size of that depends on the number of rows that you have on the node, and also the size of your keys, because we're holding those keys in memory in the index samples. In version 1.2, this was implemented as an array of longs and an array of bytes, a 2D array of bytes for the row keys. Prior to version 1.2, it was implemented by holding the objects that actually those bytes get deserialized into a decorated key, but in 1.2 it looked like this. This is a bit easier to get your head around. Again, stuff we have to hold in memory. If we look at the total size of these index samples, and along the bottom here there's millions of rows. When we get to having 1 billion rows and our row keys are 25 bytes long, looking at 230 odd megs of data that we have to hold. Now, all this is an issue because in the JVM, larger heaps take longer to garbage collect. So again, let's set a context for what we mean by larger. The default configuration in Cassandra, in the Cassandra env.sh file, is to not create a JVM heap above 8 gigabytes. Once you get above that, there's extra work that the par-new compaction process that works on the new heap has to do, because it has to look at all of the old data, all of the data in the tenured heap, sorry, to see if any of it is pointing to objects in the new heap. And also CMS is going to take longer on the tenured heap. Additionally, if you've got a large working set, large amount of memory that garbage collection cannot free, you're going to see more frequent and prolonged garbage collection, typically in the CMS collector, the concurrent mark sweep on the tenured heap. And normally, if you're looking at a graph of your JVM usage, what you want to see is that it goes up and then drops suddenly, and it looks like a sawtooth pattern. If you zoom in closely in the path where it's going up, you'll see it's a jagged line as par-new comes along, and par-new could be collecting 600 megs to a gigabyte of data. So we go up in a jagged line, and then the CMS kicks in, and that frees a lot of memory, and we drop down. To give you an idea, running with an 8 gig heap, the default is that the CMS will kick in at 75% occupancy, which is around 5.5 to 6 gigs because there's some other part of the memory that's used for the gen. And I normally like to see that in a healthy machine dropping to between 2 to 3 gigs. If it's not getting below 3 gigs a lot, I'd want to understand why, and it depends on some of your configuration settings and things, but to give you an idea, this is the sort of thing we should be able to see GC doing, making a big chunk, like dropping 3 or 4 gigs of data at a time. So let's look at some of the operational concerns. Bootstrapping is the process of bringing a new node in. It joins the cluster, it takes ownership of some tokens. Those tokens specify data that's going to be a replica for, and it talks to the other nodes that are already replicas for that data and asks them to stream data over to it so it can take ownership. Once it finishes the bootstrap process, it's got all of the data that the other node sent it, and it also has writes that occurred as soon as it started the bootstrapping process. So when bootstrap finishes, it's ready to go. And this process is throttled by a YAML configuration setting called the streaming throughput outbound megabits per second. And it defaults to 200, which is roughly 25 megabytes. And the reason that it's throttled is that this is sending data using the streaming process is a very low-level approach. It can go as fast as the disk and the network will let it. And we don't want the sending nodes to essentially do a denial of service attack on themselves and saturate their outbound network by sending data quickly to a bootstrapping node, because they're still serving requests. When you bootstrap a node with RF3, and we're not using virtual nodes here, this is pre-version 1.2, my node will come in, it will have an initial token, and that will identify one token range, but we've got RF3, so there's actually 3 token ranges that this node is a replica for. So it will ask 3 nodes, one for each of those token ranges, to send it data to Bootstrap. So we know that the sending process is throttled at 25 megabytes a second, so our maximum send rate then is 75 megabytes per second. In practice, it's going to be less than that, but that's our maximum. If we've got a 1 gig networking in place, we've got 125 megabytes per second. So there's quite a lot of headroom on our bootstrapping node, and we'd really like to saturate that guy. We can't control the time to fail, but we can control how long it takes to recover from a failure. So when we have to replace a node, we want that to go absolutely as fast as possible, and we want that process to scale as we grow the cluster. We want to get more value out of our cluster. Now, you don't always need to bootstrap. Often we do a process that internally we call a lift and shift, and this might be that we're upgrading to new hardware inside of EC2 or an enterprise data center, or moving into new networking infrastructure or something like that. We don't need to use a bootstrap process. Cassandra is pretty flexible here. We can just shut the node down cleanly, copy all of its data and config over to a new node, and start it up. And Cassandra will just see that IPs have changed, handle it all, and there's no concerns. So in this case, we're just talking about our transfer speed through the data center using rsync or something like that. So if we get 50 megabytes per second in EC2, that's probably about what I'd expect, and it's going to take us half an hour roughly to move 100 gigs. If you've got 500 gigs, multiply that by 5. If you've got over 500 gigs, multiply it by however many, and you start to see that it can take some time to do the copy. Now, disk management is one of the hardest things, I think, in deploying a Cassandra cluster. Disks don't like having more than about 75–80% of their space used. Performance degrades when you get above that on a spinning disk. If we want to store more than 500 gigabytes, we're going to need multiple terabytes of data on each data space on each node. And we could build a single volume, or we could use multiple volumes to do that. If we want to build a single volume, traditionally we'd use RAID 0 if you're on EC2. The downside of that is that if we have a single disk failure, we lose all of the data on that node. And this can be a pain. We've just seen that bootstrapping can take a while. So there's sort of a negative feedback here. Build a node with RAID 0, put a lot of data on it, congratulate ourselves that we've got a lot of space and filled it up, lose a disk because we're using RAID 0, and then go back to the beginning and have to do a bootstrap, and that can take a long time. Another option is to use RAID 10. Of course, this doubles the raw capacity requirements. Typically, we might see this in an enterprise data center where there's a standard build for machines, not coming with a RAID 10. Great for operators. They are really comfortable just replacing disks at a hardware level, but it increases the costs. You can use multiple data volumes. You could mount each disk individually and tell Cassandra about those through the data files directory YAML setting. Now again, we're talking in the context of pre-version 1.2. In that environment, Cassandra was not intelligent about how it distributed the load amongst those multiple volumes. It would just choose the one with the most free space, and so you could end up with multiple write threads trying to write SSTables as quickly as they could onto the same volume. Also, if you had a single failure in a data volume, it would shut down the whole node. You'd still have all the remaining data, it's just that the node would have an exception and shut down. And the repair process is, I know that the repair process causes problems for people, but we know it's important. The background here is that when we do deletes, we do a soft delete, we write a tombstone, and we want to make sure that that tombstone is fully replicated before we purge it off disk through the compaction process. Also, repair is the way to ensure on-disk consistency across all of your nodes. The way it works is that we calculate a thing called a Merkle Tree, and then we use that to compare differences. To build the Merkle Tree, we have to read all of your data in a particular table. Technically, we do it by reading ranges of data at a time, but let's just say we have to read all the data in a particular table. You can see this in nodetool compaction stats. It's called a validation compaction. That's because this process runs through the same infrastructure as compaction. It's throttled by the compaction throughput megabytes per second, which YAML setting, which defaults to 16. And so you can probably guess what I'm going to say is this process grows in time as the amount of data on the node grows. If you've got 10 gigs of data on disk, your repair only has to read 10 gigs of data. if you've got 1.2 terabytes, we have to read 1.2 terabytes and calculate a hash. So that's a CPU intensive operation, depending on how your machine's set up. First thing, we've got to get all this data off disk. Second thing is we've got to make the hash so we can push the CPU there. If you're on SSDs, this tends to be a bottleneck on the CPU. If you're on hard drives, this can be bottlenecked at the disk. The second part of repair is that after we've exchanged the Merkle tree and detected differences, we stream those differences using the same process that we use for Bootstrap, the streaming infrastructure. And again, this is throttled for the same reason, the Bootstrap is throttled. And we don't repair individual rows, we repair ranges of rows. That's where we detect the differences. If you've got very big rows, we could end up streaming a new copy of a very big row to a node just because another node in that token range that was checked was another row was out of sync. If you've got billions of small rows, you can end up streaming billions of small rows because one of them is out of sync. Now, compaction is a fact of life in Cassandra. It's a fact of life in any sort of log-structured merge storage engine like we have. We have this great advantage of writing new things to disk, writing new files to disk every time we flush. Takes out a lot of locks in the storage infrastructure, but it requires a compaction process. Otherwise, read performance would just fall off a cliff over time as we had lots and lots of new files to look at. So what compaction does is it looks at a particular set of files on disk, and it writes the same truth that you find in those source files into some new files. And it discards information that is no longer required. So it might be that you've done an overwrite and the previous value is no longer required, and that won't go into the new files. They have two strategies for this. The original one is called the Size TieredCompaction Strategy, and this guy just groups the SSTables by size. Files in the same bucket that is going to process are 50%, within 50% of the median of the size of the files in that bucket, and it assumes no reduction in size for the output. So if it's going to compact 4 50 meg files, it assumes it needs 200 megs of free space. So in theory, we need 50% free space on the disk. In practice, we've seen this run with less than 50% free space, although it's not recommended. Really, you should use 50% free space as a soft limit on your disk. Now, this doesn't sound as bad as it is because we know that if we get above 75%, we're going to see the throughput on our disk reduce quite a lot on spinning disk. I'm not sure on the impact on SSDs. The other strategy we have is called LeveledCompactionStrategy, and this is inspired by LeveledDB from the Google in their Chromium project. This groups SSTables together by a level, and data moves up into higher levels the more often it's compacted, not based on size, just based on some other heuristics. Inside each level, your row is guaranteed to only have one fragment. This can have a great impact on reducing the read latency. Level compaction also does a really good job in a highly mixed workload where you've got a lot of overwrites and deletes. But to do this, it requires a lot of disk I/O, approximately twice the disk I/O. And my feeling is that it requires approximately 25% disk free space. So there's some of the issues. We've dealt with those before. We've seen nodes running with over 1 billion rows. We've seen nodes running with 700-800 gigs of data. We know that there are some issues there, but we can work around them and keep those clusters healthy. One of the first things we normally do to manage memory is reduce the bloom filter size. So we change the bloom filter FP chance from 0.01 to 0.1 on some column families, and we know that that's going to reduce the size of bloom filters that we have to hold in memory. Now, this is probably going to also increase the read latency because we know why the bloom filters are there. They're there to reduce the amount of wasted disk I/O where we go and look for a row in a particular SS table that doesn't exist. We can play around with the size of the compression metadata by adjusting the chunk length. I've never really been a fan of this. This can increase the read latency because now we've got to decompress more data to find the piece that we're interested in. This is a more typical thing to do. We can reduce the size of our index samples by increasing the index interval in the YAML file, and we typically kick this up to 512, up from the default 128. So again, we think about what this is going to do. Less samples in memory. When we go to disk, a larger page that we're going to scan through to find your row. So again, this can increase our read latency. Now, if all that doesn't work, and you probably actually do this in conjunction as while you're making those changes, you can increase the JVM heap up to 12 gigs. Sometimes I've run it at 16. I would say this should be seen as a temporary measure, and the goal should be to get back to running at an 8 gig heap. If you're doing this, you can increase the new size of the heap to something keep that something reasonable at around 1,000 to 1,200 megabytes. The bootstrapping, if you've got a downtime on your cluster, or slow time, sorry, on your cluster, it might be at night or something like that, you can adjust that streaming throughput using nodetool. So you can go in there and use nodetool, go to the nodes that are sending data, set it to 0 or something high, to disable throttling or something high, and with that in place, bootstrapping will run as quick as possible, come in the morning, put it back to the 200 megabit setting so that your bandwidth is dedicated, is evenly split. Now, if we're doing a lift and shift to move node to a new infrastructure, what we'll do is we'll run a snapshot first and async the snapshot over to the new node while the original is still operational. And when it comes time to move the original node completely, we do a clean shutdown, so we disable the APIs, we disable gossip, we drain so that everything in memory is flushed to disk. And then we do an async to just get the deltas over to the new node. So we have to copy a lot less, and that node's down for a lot less. Remember, if you do that, to include the flag in there to delete files on the destination that no longer exist on the source node. Disk management, if you can use RAID 0 and over provision, I mean just have a little bit more than what you expect, not a huge number. And if you're in EC2, you don't need to do this because Amazon's already provisioned thousands of nodes and you can get one within a few minutes. You can just use RAID 10 and accept the additional costs. Again, typically we'll see RAID 10 in an enterprise setting where they're a standard build. Now, repair really is something I'd encourage everyone to use unless it's taking several days to complete because you've got so much data. If you really need to, you can only use it when data is deleted, in which case I'd recommend that the consistency level is not 1, it should be quorum to ensure that your data is written to at least 2 nodes. You can also do sort of more frequent, smaller repairs. You don't have to repair a whole key space. You can run a repair at a table level, or you can run a repair on individual token ranges if you've got a very big table. This was on the JMX interface for a while. It got moved onto the nodetool repair function, nodetool repair command line tool. I can't remember exactly what version it got moved on there, but you should be able to use it. Now, compaction, you're going to over-provision the disk capacity when using Size Tiered. Typically, if I'm on an EC2 node, an M1XL, which used to be the standard build, you'd have 1.7 terabytes of data and you'd use 500 gigs as the soft limit. So in that case, we've sort of over-provisioned. If you're running low on space, there's a little hack you can do that can help, which is if you adjust the min compaction threshold and the max compaction threshold and you drop those down, you reduce the number of files that it's going to compact. It becomes more aggressive in the sense that it runs more frequently, but instead of compacting 400 meg files, it will only ever compact 2, and so it only needs 200 megs. If you're really in a bind, that can allow compaction to make incremental improvements until it frees more space. Level compaction is a great thing to use if you've got a lot of overwrites, because Size TieredCompaction doesn't handle those very well, or if you care a lot about latency, about read latency. Use it where appropriate. As I said, it takes approximately twice the disk I/O. If you're on spinning disk, I'd use it sparingly on just particular column families that need it. If you're on SSD, you can go crazy. So we've got a bit of background about why some changes may have happened in 1.2, things we'd have to work around if we're still on before 1.2. Hopefully now convince you to be using at least 1.2 or 2.0 and give a bit of understanding about why changes are going on. So version 1.2 moves the bloom filters and the compression metadata off the JVM heap. Version 2.0 moved the index samples off the JVM heap. These still take up memory. They're sitting out there still, but the garbage collector doesn't care about them, and we've reduced the size of the working set. So now our CMS, which before would have to go along and couldn't free up enough space, perhaps because the bloom filters were sitting there, now has loads of space. So we can get a much better sawtooth pattern. We have lower pauses in our process. Virtual nodes were added in version 1.2, and one of the reasons they were added was to improve the performance of the Bootstrap process, so that when you get up to having 30 or 40 nodes in a cluster, you can get some value for having all those nodes. vNodes, instead of having one token range per node, have 256 by default. So each node is a replica. Each node shares replicas with so many other nodes. Essentially all nodes in the cluster share data with another node. So now when we bootstrap a new node in, it has 256 token ranges times the replication factor that it needs data for, and it goes and talks to lots of other nodes in the cluster. So if we're bootstrapping in this environment and we've got 10 nodes and we're adding another one, all 10 nodes can contribute a small amount of data, and it becomes a lot easier to saturate the incoming node. We also have JBOD support, just a box of disks. This really did improve the way that we handle multiple data volumes. So you can mount them all up individually, list them in data files directory just like before, but now when we go to write to one, it's a lot more intelligent. It will write to the volume that has the most space that isn't currently being written to. So we don't get a thundering herd going to a volume that suddenly got a lot of space because compaction freed something up or something like that. Together with this new setting called the disk failure policy, this makes this a real viable option. So the ignore setting for disk failure policy makes it work like pre-version 1.2, which is the exception isn't handled, server shuts down. The stop setting says, okay, when you get an I/O exception reading or writing to disk, handle the exception, log it, mark that that data volume should no longer be used for reads or writes, make that information available via JMX, including there's a JMX push notification interface there. And then it puts the node into a suspended state. It disables the thrift and the binary APIs, it disables gossip, and the process keeps running. So essentially it drops out of the ring, logs and makes all the information available about why it did that. Your operators can come along and make a decision about what they want to do. The best effort setting does all that, except it doesn't shut it down. So detect an error, isolate that volume and say no longer do it, no longer read and write to it, log it, the information, make it available via JMX and the JMX push notification, but keep running. So if you've got 4 disks, you suddenly lost a quarter of the data on this node, and it's going to keep on running. If you're using CL quorum, there's no problems there. The quorum process for your reads and writes will detect that this node that's suddenly lost some data is returning data that doesn't match, and will repair that. If you're using CL1, you're going to get some stale data. In the best effort, it's really good. You can then run repair and repair that data. You could replace the disk and run repair if you wanted to. And the process that you go through with best effort is roughly the same process with stop. You can, when stop happens, you can make a decision, okay, do I just want to light the interfaces on this again, and we use CL quorum and we'll start off a repair and we'll fix it, or do we want to take some other action, like bring the node down? A couple of things that are coming up in version 2.1. There's an improvement to the repair process. Our SSTables on disk are immutable. Once we've calculated the Merkle Tree, in theory, there is no way it will ever change, so we shouldn't have to calculate it again. Ticket 5351 takes that idea and makes improvements so that repair takes less time. Has some impacts on how compaction works, and we'll just have to see how that process works when we bring that in for new nodes upgrading to 2.1. And I mentioned at the beginning about bloom filters that there are guesses as to how many rows are there when compaction's running. Particularly in workloads where you've got a lot of overrides, you could compact 4 files that had 1 million rows in them each and end up with one file that has 2 million rows. But the compaction process would allocate a bloom filter to fit 4 million rows, and so wasted half the space. Ticket 5906 uses a piece of software called the hyperloglog to make estimations about the distinctness of the rows and then allocate bloom filters appropriately so there is less wastage. So that's a look at what happens when you take Cassandra beyond 1 billion rows, beyond 500 gigs of data per node. Hopefully that's also given you some background understanding about why changes happen in Cassandra, why were the bloom filters taken off JVM heap and things like that. So when we see some new features come through, you can understand why they're there. So I'd like to hand over to Christian now, and any questions.
Hi there. Thank you very much, Aaron. Can you hear me okay?
Yep, still there.
Okay, great. So just a reminder to please post your questions in the Q&A tab inside of WebEx. We're getting a lot of good questions coming in. And on your screen right now, you'll see our upcoming webinars, March 6th. Patricia Gawler, also a member of the Last Pickle. And then on April 3rd, we have Cassandra at Lithium. Lithium is a social interaction platform for large enterprises. I will answer Sabroto's question up front because he is asking where we can get a replay of today's recording. We always post the slides and the recording to Planet Cassandra within about 24 hours. So this time tomorrow, they will be on Planet Cassandra. So, Aaron, you ready for some Q&A here?
Let's do it.
Okay. Alan asks, is JBOD useful on EC2 with a DataStax AMI? I mean, using RAID 0 when writing to RAID 0 Cassandra, aren't we already writing multiple disks? So I don't know if that's one that you can take, or if we should, you know, get someone from DataStax to respond to that.
No, I can handle that. So yeah, if you're using RAID 0, you're using multiple disks. And the reason, one of the reasons we have RAID 0 is that it gives us a nice big data volume. And the other reason is that it improves performance by striping the writes across multiple disks. Personally, I think if I was using an M1 XL or any Amazon instance with spinning disks, I would still use a RAID 0 to get the best performance you can, and the highest amount of disk ops out of that volume. If I was using, say, one of the new i2 instances that use SSDs, I'd consider going to JBOD. I don't understand precisely how they could fail, one fail and not the other, so you probably want to do some research on that. But I would consider using JBOD just because it's there and it's useful if you have a single disk failure. It can keep on working. One of the downsides of JBOD is that you don't have a huge, one big data volume, so compaction can get a little bit concerning when you get too much data on the node. But in the normal case where you don't overload the data on the node, it should be fine.
Great. John asks, question about leveled compaction. I'm working with time series data. I have a couple of column families that are queried heavily every hour when computing rollups. Would these be a good candidate for leveled compaction?
I would, without knowing too much more, I would probably say no. I'm going to assume that your rollup process is not a latency sensitive query. So by latency sensitive, I mean you're in an API request, you're doing a page refresh or whatever it is. I'm going to assume it's a background process. Also, if you're doing time series, you're probably not mutating your data. So I'm guessing you're not doing overwrites, you're not doing deletions, so it's a append-only data model normally. So it's a sort of data model that works well with size TieredCompaction.
Okay, and then Wade is asking a little bit of clarification here. I didn't understand the repair Merkle Tree compare improvements.
Right, so our SSTables on disk are immutable. So once we've read all the data in a particular SS table and calculated the Merkle Tree, which is a tree of hashes, so the intermediate nodes are a hash of the hashes on the nodes below them, and the leaf level nodes are a hash of a range of rows. Once we've calculated that, it will never change. And currently, what we do is we calculate that again and again and again. You could have a 100 gig SS table on disk, and every time you run a repair, we'll go and calculate a hash on that guy, which is a waste. So what that ticket in 2.1 does is take advantage of that and store those Merkle trees. Then there's a bunch of clever logic in there about understanding how what SS tables have been dropped and which ones have been created, and that impacts on compaction a bit. So what it's going to do is reduce the amount of time it takes for the validation compaction on repair. So if you do a full repair on Monday and then you only write 10 gigs of new data on Tuesday, we're only going to have to calculate the hash on the new 10 gigs of data.
Okay, thank you. Why do we have a limit of 5 terabytes per node?
So again, the Bootstrap process, even though now it's better, and there's probably there are some physical limits in Cassandra, some just how high a long will count or something like that. But if you've got 5 terabytes on a node, what will you do when that node fails? How will you build a new node? How quickly will it take you to get 5 terabytes on there? There's probably not a lot of physical restrictions, like, okay, you're going to overflow this long, so you can't have this much data on it. But it comes down to things like, how long is it going to take you to replace the node? How long is it going to take for a repair to run? How long is it going to take to do a backup of get stuff off that node? That sort of stuff. The mostly operational management things, sometimes things like bloom filters or that sort of stuff can kick in and become a concern. So even though, let's say you got 5 terabytes, well, we've got like 5 billion, let's say 5-6 billion rows on that node. The bloom filters at 1 billion. If we're using Size TieredCompaction, we're looking at 1.2 gigs of data. So now we're looking at 6 or 7 gigs off heap data for the bloom filters. That can take a while to load. And now we're looking at 10, maybe 20 gigs of data, memory to hold the JVM and all the associated off heap information. So now your nodes are getting bigger, just operational concerns.
Okay, great. is there a practical disk size limit for spinning disks on Cassandra 1.2? That's from Sumia.
I don't think so. You know, my concern with spinning disks is always how fast they spin. So typically you get a larger single volume, like you get a 1 terabyte or a 2 terabyte. It might be a slower spin speed, so it might be down at like 7,000 instead of 12 or 15. Also, given the choice, if I had to put like 2 terabytes of disk on something, I'd rather have a couple of them. I'd rather have 2 1 terabytes or something like that, because now I can use RAID 0 and get twice the disk I/O, or even using JBOD, I can write to one disk and write to another disk. So I'm splitting my writes and effectively using the disk I/O that they provide. So all things being equal, you probably want to avoid having just one disk for the data. Having multiple disks gives you increased disk IOPS.
Okay, great. And Wade is asking about, for repair, you didn't mention secondary index rebuild. Could you talk a little bit about that?
Yeah, I probably did mention because I don't use them a lot. So when we do, in the streaming process, when we bring over some data, so I'm just trying to remember the code.
Well, maybe is there a reason not to use them? Why don't you use them very much?
It's mostly because I started using Cassandra before they were there, and there are some concerns. Their secondary indexes are good in some situations. You might have some data model which is, hey, this query only gets used by people on the internal portal or CRM type people. It doesn't happen very often, and we just need some support for it. So that's a good use case for secondary indexes. If you've got a query that is something that's part of a hot code path, like, okay, this happens 30% of the time we do a page refresh, this happens, this gets called all the time, then I think it's best to model that as a first-class entity in your data model. Secondary indexes, when you do a query, we have to go and ask a lot of nodes. We don't know exactly what node has your data, so they have some reduced performance there, and they have some reduced availability because they have to ask so many nodes. When we do a Bootstrap process, we will rebuild the secondary indexes, and when we do a streaming process, we will rebuild the secondary indexes as well, I believe. Internally, secondary indexes are just hidden tables.
Okay, great. So Michael's asking, and by the way, Michael, there's some data out there by Netflix about how much data they store in Cassandra, but Aaron, what's the largest data capacity you've dealt with in Cassandra? Roughly how much disk per node and how many nodes?
So we've dealt with systems into the multiple, in around 10-ish plus terabytes. A number of nodes is difficult. The size per node tends to be a factor sometimes of the performance that you want to get out of it and the type of data. So I would just go back to those guidelines of if we've got a lot of data that we have really low latency requirements, we want to be a terabyte-ish of data per node in post version 1.2. If we're mostly just writing data and doing back office type reads, I think you could put more data per node. If you've got operational concerns about how quickly you can replace nodes, again, say you're in advertising retargeting or something like that, those guys normally have really big throughputs. We want to be able to replace those pretty quickly. So it's kind of a balance between all those issues.
Okay, great. And Kalman asks, has off-heap memory changes helped with the max column families per cluster issue?
Okay, with the max column. It will have helped a bit, but the concern there, so each column family, each table takes up some memory. That has a mem table that stays on the JVM heap. But what it also does is when we do the calculation to work out when to flush the disk to detect how much memory we've used, one of the factors in there is the number of column families. So we will flush the disk more frequently. And when we flush the disk more frequently, there's the extra I/O of flushing the disk. It creates more compaction, and so you use more disk I/O there. So I don't think it fixes those problems. Now, you can have multiple tens of column families. I've admin some systems where they're in the 400 plus column families, and it's just really painful to do anything. If you need to make a across the board schema change, it's 400 updates, and that can take a long time, like half an hour or so. When you're trying to move things around,
oh no, we lost New Zealand.
Oh.
Aaron, we lost you momentarily.
Oh,
Skype
sorry about
failed you.
Yeah, so I was just saying it helps, but there's still the more issues of too many column families, use too much disk I/O, and when you're adminning a system like that, you end up with lots and lots of small files that are hard to copy around quickly.
Okay, Annie asks, will repair performance improvement bug fix, which is targeted for 2.1, also be fixed in 1.2? Do those patches go back and get applied to previous versions?
No, they don't. They're just all going forward things. So what you're going to probably nowadays in I'd say we're at 1.2.15, and that guy's essentially baked unless there's a bad problem. I'm not going to get many updates. 2.0 is at 5 or 6 now, so that guy's pretty much ready for prime time. And once we get 2.1 into general release, then the chances of anything going into 1.2 are pretty low. And changes like the improvement to the Merkle Tree management are big changes, and it's just too much effort to backport them.
Yeah. So Alan asks, what's the max size? What's the difference between max size in a 1.2 node and a 2.0 node?
So not a lot between 1.2 and 2.0. A lot of those improvements came in 1.2. 2.0 took the index samples off heap as well. So I'd say it's pretty much the same size.
So Aaron, this one is probably a broader, like, consulting question. So this one's from Jan, but if there's a very short answer, great. If not, maybe just go one-on-one with Jan afterwards. I have a database that will contain around 50 to 75 billion rows in the future, which is spread over 2 tables. How stable would it be, and does it make sense to use a structure like that?
Yeah, that doesn't sound any alarm bells to me. We've talked about what happens when you have lots and lots of rows. So the best thing you can do is jump on AWS and get a decent node like an i2 node, and just fill it with data and see what it looks like. You can then poke around and look at the memory usage and disk usage and things like that. But wanting to store that much in 2 tables and it sounds fine, you'll probably end up with a few nodes in your cluster.
Okay, great. So the next question I can take, it's a doc question. It's from Vedant. You've done a great job documenting process for installing Cassandra on EC2. However, there's very little documentation on the errors. For example, I'm getting a no user data available error, but I cannot find any doc to resolve it. The best thing to do and I was just looking it up, DataStax's documentation team has a Twitter handle. It is at DataStaxDocs, at DataStaxDocs. You know, tweet them that question, and someone will get back to you.
Let's add that if you're using the AMI and the pre-built script to install that, it sounds like the user data is the stuff you kind of type into a little text box. Sounds like it couldn't find that, so just double check that you've actually put in there the number of nodes and things. Okay,
great. Thank you. Luis says, hi, thank you very much for the talk. My question is, can you tell us about the suitability of EC2 instance types for very large data? Are memory optimized instances better than storage, SSD optimized instances better for an intense read scenario?
Yeah, so we used to always say use the M1XLs because they were kind of the best. There's another machine, so I'm just trying to grab the name here of, which has, it's called an M24XL for memory, and that has 60 odd gigs of RAM and 2 800 gig disks on it and lots of cores. So that can be a good situation where you've got a large working set because you've got 60 gigs of memory and you can have a good page cache. Now the new i2 instances really are good. They've got a lot of cores, and we like having CPU cores to do things like have a high write throughput. Then you can generally get 3,000 to 4,000 writes per second per core on a node. We also like it for compaction because the compaction is going to sit there and run. It's going to take up one core, so it's good for that. They've got a lot of memory. There wasn't always a huge amount of memory on those M1XLs, so they're in the 30 to 60 range, and they've got SSDs, so they've got loads of performance. You get them on a 1-year reserved price. They're competitive or below. I think, yeah, a 1-year reserve price, they're below an M1XL on demand. So if you need high throughput and you need a lot of reads, I would be using an i2 instance, and I'd be looking at my data model to see where I could use level compaction, because that's going to reduce your read latency. And there's a good blog post, a couple of good blog posts on the DataStax blog about when to use level compaction.
Great. We've probably got enough for 2 more questions. Mark asks, with the large size and immutability of CFS blocks and the custom CFS compaction strategy, is a much higher data volume per node practical?
Again, it comes down to what you do when the node fails and how you're going to replace it. So you can put as much data on the node as you have disk capacity, but what do you do when that node fails? Or you want to upgrade and you want to move to another node. So I do think that you need to look at it from that point of view.
Okay, great. And Majid asks, does Cassandra have any features like table spaces in a relational database? Is it possible to move files containing Bloom filters and compaction metadata to SSD and keep actual data in normal spinning disks? You can't separate the components of an SS table, but what you can do is, and this was added back around version 1.0 or 1.1 when SSDs were still super expensive. The layout on disk is that there's a directory for the key space and there's a directory for each column family. So what it used to be was we'd say, oh, okay, you've got some SSD and some hard drives. Okay, mount these up. Now what we'll do is we'll put in some symlinks in place so that the column families that you're really sensitive on performance on can go on SSD, and the column families that you're really sensitive on, that you're not so sensitive on, can go on hard drive. And I think by the time you make any sort of change, such as, okay, can we split the SSD components, these things we don't read much, like the Bloom filters over here, by the time that came in and that was bedded in, you'd probably just be on SSDs.
for everything.
Okay, thank you very much. And Aaron, thank you very much again for today's presentation. Looking forward to Patricia's, is that next week? Yeah, it's next week. On the screen right now, if you are interested in presenting at the Cassandra Summit, the call for papers is open. And also we will begin selling tickets very soon for that. So make sure to come along. It is a great event. And then also, if you want to continue your Cassandra learning, you can take the course at the link on your screen, datastacksacademy.elogiclearning.com. That is free training. So, Aaron, thank you very much. We'll see you next time.